Hello everyone, today we'll talk about the solution to the problem largest combination of bitwise AND greater than 0. Since bitwise AND is a bitwise operation, we want to look at the numbers in their binary representation and think about bit positions in that representation. So if we have some numbers, their bitwise AND, of course, at every position, this of course should be the same length here, at every position it has a 1 only if there are only 1s above. If there is at least one 0, then the bitwise AND has a 0 at that position. And that's the typical things that we know about bitwise AND, is that if we were, for instance, being asked to choose some subset of numbers such that the bitwise AND of that subset is maximum possible over all the subsets, then it would be realized by a single element subset, because adding new elements to the set that we've already chosen can only flip bits that were previously 1 to 0, and of course flipping 1 bits to 0 reduces the number. So that is one thing that we know about bitwise AND. And in this case, since we want the bitwise AND to be greater than 0, what does that mean? Well, 0 has zeros on all positions. Whenever we have at least a single 1 at any position, then our bitwise AND is greater than 0. Okay, so our largest subset that we can take has to have a 1 at some position. What does that mean? That means that if this is the position, all the numbers in that subset have to have 1 at that position. And we don't care about any other positions. So one way that we can determine the best subset is to think about every possible position. There are of course not that many, because every position is the next power of 2. So essentially the bit length of the number is the number of positions, so this is a very small number. About 30 will typically be sufficient. In this problem, I think 24 would suffice as well. And we can, for every position, count the number of values in our candidates array that have that bit position set. Because we can take all of those numbers together, and we are sure that their bitwise AND will be greater than 0, because they will have a 1 at that position. So, in order to do it, we can either maintain the counts in an array and go through all the values for every value, and for every power of 2, of course, we can run a while loop until our power of 2 becomes bigger than the number, because then we can be sure that it never has that bit set. We just check if the number has that bit set. So we'll be maintaining the value of those powers of 2, so p will be equal to 1, 2, 4, 8, and so on. And I will be the index of that power of 2, so the exponent 0, 1, 2, and so on. So, to check if a given number has that bit set, we can use binary AND with our number and this power of 2, because the power of 2 is just a number that has a single 1 at a given position, and that's exactly what we're interested in. So that bitwise AND will be 0 if v does not have that bit set, and 1 if v has that bit set. That's what we want. If it has that bit set, we increase the count for that power of 2, so that's why the value I is necessary here. We increment I, and we multiply p by 2, and multiplication by 2 is the same as bit shifting to the left by a single position. And since this is exactly just a single 1 and we want to shift it to the left, that's probably the best way of writing it. But of course, you can also just multiply it by 2. At the end, over all those counts, we return the maximum, because the counts of 0 is how many numbers have the first bit from the right set, so the earliest bit. The next count value is for the next bit, and so on. And if you want to hone your Python skills, you might think about how to write a short and elegant, well, maybe not that very elegant, but a short one-line solution to this problem. And as a hint, it will probably be more convenient for you to swap the order of those two loops. Because swapping that order will probably, well, it doesn't change the correctness for our solution, but it might be better. One order might be better than other, because for instance here we go through all the values and we have a different single variable or two variables that increase. And if we swap the order, then we would have we will be going through the candidates array for every bit position. So that might be slower, maybe it isn't. If you want to check, then you can check it. And if you check the version with reversed order, then try to make a one-line solution, because then it should be pretty easy.